So today we'll be talking about magnetism, or more specifically, we'll be talking about how two parallel wires will interact when they have current running through them. So we have two parallel wires. Let's first consider the case where we have two wires in which they have different currents, namely an I1 and an I2, but the currents are all running in the same direction. In this case, we'll say up. Now we want to consider what force does I2 exert on I1? Because we know that there is going to be a current, with any current or moving charge, we're going to have a magnetic field. So we can draw, by using the right-hand rule, we can see that the magnetic field will run in this direction, namely on the right side of our wire number 2, it's going to go into the page. This means, the x means that, by the way, that the vector, in this case the magnetic field vector, goes into the page, and on the left side we find that it goes out from the page. So here the magnetic field comes out of the page. And in both of these formats, the x and the dot, we find that they are going to be perpendicular to the surface of the page. So once we've established that, then we know that there is going to be some magnetic field, we'll call this B2, that our wire number 1, the current going through wire number 1, is going to experience. Now we know that the force is going to equal to the current of our object, namely I1, times L, we'll call this distance L, cross B. And in this case, B is going to be the external magnetic field, which is experienced by wire 1, so namely this is going to be B2. So then what we find here is that we have this relationship for what the force is as a result of these two wires coming together. So this is the force that is acting on wire 1. Now we want to find an expression for this B2. Well, what we know is that if we can draw from the top down, here is our I2, and our I2 is coming out at us. And we have so by using our right-hand rule, we find that our magnetic field is going to go counterclockwise. So this is the direction of our magnetic field, B2. So if we say that these two wires are some distance, how about r, apart, then we want this our circle that we choose for the distance that we are away from I2. We want this distance to be r, because we want not only an expression for B2, but B2 specifically where it is experienced by wire number 1, which is here. So we have Ampere's law, which is that the single loop integration of our B dr is going to equal to mu 0 times I. In this case, the integration of B dr is just going to equal the circumference of our circle. So we have that 2 pi r times B2, and here it's just the magnitude because we have dot dr is going to equal to mu 0 I. And thus we find that the magnitude of our magnetic field is mu 0 I. In this case, I is going to be I2 because I2 is what is causing this magnetic field, divided by 2 pi r, which is the circumference. And so this is the magnitude of the field that our I1 wire is going to experience. Now, once again, as we have mentioned before, the magnetic field that is caused by our second wire with current running through it, its magnetic field is going to point out of the page, when toward us, out of the page, on the right side of our I1 wire here. So then what we find is that if we draw a diagram, we have this is the direction of our current I1, and it's pointing out of the page, so that's the direction of our magnetic field that it's experiencing. And since we want to cross these, we can also draw it like so. How about if this is the surface of our page, so this is our page, we have that I1 is pointing upward, I1, and B2, this is B2, is pointing out of the page. So when we take the right-hand rule of I1 cross B2, we find that it's going to go like this. So our resulting vector is just going to be pointing to the right. And that's going to be the direction of the force. Now, what does it mean if it's pointing to the right? Well, we have our two wires like so, and this is B2 coming out of the page. Here is I2 and I1 both moving forward, and we've established that the force that our our wire on the left experiences is going to point towards the right. And what we find is that means it is being attracted to our second wire. And if we do the same thing for our second wire, we find that in this case, when we do the same thing for I1, we have that it's going into the page. We have that B1 is going into the page. So we have for I2, we have I2 going upwards, and then B1 going into the page that it is experiencing. So once again, if we do a right-hand rule, we find that the resulting vector, when we take the cross product, is going to be pointing to the left. And thus we find that these two forces, since forces must be equal and opposite, since action and reaction, we know that these forces are going to be equal in magnitude, and the force that is acting on the left is pointing to the right, and the force that is acting on the right is pointing toward the left. So we find that when the currents I1 and I2 are facing in the same direction, they will be affected by an attractive force. So attractive force. But this is only when the I's are in the same direction. So same direction.